In this part, we will talk about the limit at infinity. So we have learned the infinity limit, do you remember? Which is about the vertical asymptote. So if you have a vertical asymptote, right? This is the vertical asymptote for the curve. So we care about the limit x approaches c of f of x, right? Which is positive infinity or negative infinity, right? H plus c plus approaches c plus, or x approaches c minus, or f of x equals positive infinity or negative infinity. If one of them is true, then we can say x equals c is a vertical asymptote. Okay, so now we want to look at the horizontal asymptote. So this is a horizontal asymptote for a curve. The horizontal asymptote is actually, we have a curve, right? When x is increasing to infinity, if the curve is very close to this horizontal dashed line, then this dashed line is called, this dashed line is we denoted by y equals L, okay? So this dashed line, which is actually the y equals L, is the horizontal asymptote. The similar for the other side, if you have this one, okay? So if x, this is x approaches positive infinity, if x approaches negative infinity, then if the curve will approach the dashed line, this dashed line y equals L would be a horizontal asymptote. So this is the horizontal asymptote. So the horizontal asymptote talk about the asymptote. The horizontal asymptote is talking about the end behavior of the functions. So when x approaches infinity, when x approaches negative infinity, so this is called the limit at infinity. So in other words, we need to look at the limit when x approaches positive infinity of f of x, and when x approaches negative infinity of f of x. Okay. So this is the, so now let's look at the formal definition of the horizontal asymptote. So we say a function f of x is a horizontal asymptote y equals L if either limit x approaches positive infinity of f of x equals L, or limit x approaches negative infinity of f of x equals L. So you can see that it's very important to know how to calculate the limit when x approaches infinity. Right. So here is some typical way we will see that. Let's use some examples. Okay. Now let's look at this example, a typical example to see how to calculate the limit at infinity. So this is the example. 3 times x to the fifth minus 4. So you can see that when x approaches infinity, that means x is a very large number, right? What is the behavior of this function? What is the behavior of this function? So the first thing we needed to do is we needed to determine the highest power of the numerator in the denominator. The highest power of the denominator, which is x to the fifth, right? So x to the fifth is the highest power. Highest power in the denominator. Then we divide. This is the first one. The second step, we divide x to the fifth. We divide the numerator and denominator by x to the fifth. So you will see this one would be, take the limit, x approaches infinity. We divide by, it will not change our result, right? Because we divide by the same number. Then you will see it would be x to the infinity. So this is the 2 over x to the fourth divided by x to the fifth, so it would be 1 over x, right? So it's 2 over x minus 1 over x cubed, each term divided by x to the fifth, minus 8x to the fourth, right? So this would be 3, and this is minus 4 over x to the fifth. Then you will see when x approaches infinity, x is a very large number. Do you remember that? If a fraction, the denominator is very large, then this fraction is very close to 0. So if x approaches infinity, so this term will approach 0. This term would be a 0. This term would have the limit 0. And this is 0. So what you have? You have 0 plus 0 plus 0. We take the limit for each term. 3 minus 0, which is 0 over 3 equals 0. Okay? So this is the typical step. The first step, you need to locate the highest power in the denominator. Then we divide the top and bottom by this highest power, x to the fifth. Then do the limit. Okay? So now let's look at another definition, another example. The limit x approaches negative infinity for x squared plus x to the 6th over 1 minus 5x cubed. So for this limit, again, the highest power in the denominator is x to the third, right? So we divide by x to the third for the top and the bottom. The limit x approaches, don't forget this limit sign when you do the calculation. So you need to divide by x to the third for the top and the bottom. Then you keep everything the same, right? Then you do the calculation. So this would be The numerator is 4 over x plus x cubed. This is 1 over x cubed minus 5. Then you will see that if you take the limit x to the negative infinity, so the denominator is very large, right? Negative infinity. So this would be 0. This would be 0. What about x to the cube? If the negative infinity, then raised to the power cube, this would be what? Still negative infinity, right? Over negative 5. So negative infinity divided by a negative 5 would be positive infinity, right? Let's look at more examples. This is the limit x approaches positive infinity. This is x squared over square root x cubed plus x plus 1. Okay, so for this one, you can see that the highest power in the denominator. So for the inside, that's under the square root, the highest power is x to the cube, right? But we have the square root. Square root is the 1/2 power, right? So we can see the highest power in the denominator is x to the 3 over 2, 1/2 power, and it's cube, right? So it's 3 over 2. So we divide this one, so this is the limit involving the radical sign, so you should be careful, okay? So this is the x to the cube, and this would be the square root, so it's x to the 3 over 2 would be the highest power in the denominator. So we divide this x to the 3 over 2 on the top and the bottom. So x squared divided by x to the 3 over 2. This is square root x cubed plus x plus 1 divided by x to the 3 over 2. Right? Then you do the calculation. This is the limit x approaches positive infinity. So this one is actually what? 2 minus 1/3, so it's 1/2 power. 1/2 power, which is the square root of x, right? And this one, we should put this term inside the radical sign, so you need to square it, right? So this would be x cubed plus x plus 1 divided by x cubed. So you should be very careful for the operation under the square root. So if you're not familiar with that, please go to review it. So you will have, this is the x to the 1/2, this is square root, this is 1 plus 1 over x squared plus 1 over x third, right? So if x approaches negative infinity, positive infinity, this would be 0. This would be 0. But the numerator, when x is infinity, you take the square root, it's still infinity, right? So your result would be infinity over 1 plus 0 plus 0. So this would be infinity. So be careful when you have the radical sign. So here is other examples for the function when x approaches infinity for the exponential function, like e to the x, right? So this would be the power will increase forever for a large, very large number, so this would be infinity, right? If x approaches negative infinity of e to the x, so that would be 0. Why? Because it's a negative infinity, so you can, this is our draft paper, negative infinity, right? So it becomes 1 over e to the infinity. E to the infinity is infinity, so 1 over infinity would be 0. Right, so this is if you don't believe that, you can draw the graph for the e function. This is the e function, right? This is the e function. Y equals e to the x. When x approaches infinity, then this curve will increase forever, right? When x approaches negative infinity, this curve will go down, but approaches y equals 0, so which is 0. So have the 0 horizontal asymptote. So this one, 0 horizontal asymptote is, y equals 0 is the horizontal asymptote for the e to the x. The similar thing for the natural log. Another example is the natural log of x. Natural log of x is given by this one, right? So the limit x approaches positive infinity of natural log x would be infinite because it will increase forever. So there is no horizontal asymptote. And here x should not be, this one does not exist because x does not exist because x cannot be negative number. Okay, as you see from the graph, it's always positive number. So this is the domain for the natural log of x. Here, this part must be positive. Okay,